The supernova explosion that will one day destroy Betelgeuse is one of the most violent and energetic events the universe can produce. As the star's core collapses, it doesn't just disappear. It compresses to a point of maximum density and then bounces back. This rebound sends a titanic shockwave, an unstoppable wall of energy and matter, racing outwards through the star's neatly layered onion-like structure at a significant fraction of the speed of light. As this shockwave rips through the star, the immense temperatures and pressures, far hotter than anything the star experienced in its stable life, trigger a final, furious, and widespread wave of nuclear fusion. This is known as explosive nuclear synthesis. In these fleeting, violent moments, all of the heavy elements in the universe that are more massive than iron are created. Every atom of gold in a wedding ring, every atom of silver in a coin, every atom of platinum, mercury, and uranium on Earth was forged in the heart of a supernova explosion, just like the one that awaits Betelgeuse. We are quite literally made of the ashes of exploding stars. The shockwave is a creative force, seeding the cosmos with the raw materials necessary for building new stars, new planets, and eventually, new life. From our distant vantage point on Earth, the first few hours of the explosion will be invisible. The cataclysm begins deep within the star's core, and it takes time for the shockwave to travel to the surface. The very first signal that the end has come will not be light, but a massive, nearly instantaneous burst of subatomic particles called neutrinos. The core collapse releases a flood of these ghost particles, which barely interact with matter. They will stream out of the star and travel through space at nearly the speed of light, passing through the star's outer layers, through the vacuum of space, and even through the entire planet Earth as if it were empty space. Our only warning will come from massive underground neutrino detectors, such as the Super Kamiokande in Japan, which will register a sudden spike in neutrino detections from the direction of Orion. This neutrino burst will arrive several hours before the visual explosion, giving astronomers their one and only heads up that the light show is about to begin. When the shockwave finally reaches the surface of Betelgeuse, the real spectacle will start. The energy of the explosion will be unleashed into space as a blast of light of unimaginable intensity. From our perspective on Earth, a familiar, dim, red star will suddenly and spectacularly brighten. Over the course of a few hours, it will grow in intensity until it is one of the brightest objects in the sky. At its peak, which could last for several weeks or even a few months, Betelgeuse will be as bright as a half moon, and perhaps even as bright as a full moon. It will be easily and brilliantly visible in broad daylight. At night, it will be bright enough to cast visible shadows on the ground. The constellation of Orion will be temporarily and spectacularly disfigured, its familiar shoulder replaced by a new, dazzlingly bright celestial lamp. It will be an event so bright and so obvious that it will be impossible to miss, a celestial spectacle that will captivate the entire human population. After its peak, the supernova will begin a slow, graceful fade. Over the course of many months, it will change color, likely from a brilliant blue-white at its peak, fading through yellow, orange, and finally back to a dim red before disappearing from naked eye view altogether. In its place, powerful telescopes will be able to see a beautiful expanding cloud of gas and dust, a supernova remnant, the gravestone of a once mighty star. The obvious question, of course, is whether this spectacular event poses any danger to us on Earth. The answer is, thankfully, a definitive no. A supernova is a lethal event for any planets in its immediate vicinity. The blast of high-energy radiation, particularly gamma rays, would sterilize any life within a kill zone of about 50 light-years. But Betelgeuse is a distant neighbor. The most recent and accurate measurements place it at a distance of about 642 light-years. We are more than 10 times farther away than the kill zone. At this safe distance, Earth's atmosphere and magnetic field will easily protect us from any harmful radiation. We get to witness the entirety of the magnificent light show without any of the danger. The reason for the recent surge in excitement about Betelgeuse's impending doom was an event that began in late 2019. Astronomers who monitor the star noticed that its regular cycle of dimming and brightening was behaving strangely. The star began to fade, and it kept fading, far beyond its normal minimum. By February of 2020, Betelgeuse had faded to less than 40% of its usual brightness, becoming dimmer than at any point in over a century of modern observation. It fell from its position as one of the 10 brightest stars in the sky to barely making the top 25. The change was so dramatic, it was easily visible to the naked eye. The familiar shoulder of Orion looked strangely muted. This great dimming, as it came to be called, sent a wave of excitement and speculation through the astronomical community and the public alike. Was this it? Was this the pre-supernova dimming that some models predicted as the star's internal engines sputtered before its final collapse? Telescopes all over the world were trained on the star, gathering data across the entire electromagnetic spectrum. After months of intensive observation and analysis, using powerful instruments like the Hubble Space Telescope and the Very Large Telescope in Chile, astronomers pieced together the likely answer. The Great Dimming was not the prelude to an imminent explosion. Instead, it was a surface event. The current consensus is that Betelgeuse, in one of its violent convective upwellings, ejected a huge plume of hot gas from its surface. As this gas cloud traveled away from the star, it cooled and condensed into a massive cloud of stardust, mostly fine grains of silicate dust like soot. This self-made dust cloud then drifted between the star and us, temporarily obscuring our view and causing the dramatic dimming. In essence, Betelgeuse had a colossal sneeze and we witnessed it blocking its own light. By the spring of 2020, the dust cloud had drifted away, and the star returned to its normal brightness. So, if the Great Dimming wasn't the final warning, when will Betelgeuse explode? This is the central, tantalizing question, and the honest scientific answer is profoundly humbling. We do not know for sure. The behavior of the star, including its pulsations and massive ejections of material, tells us that it is undoubtedly in the final stages of its life. It has likely exhausted the carbon in its core and is burning through its final frantic reserves of heavier elements. But final stages on a cosmic timescale is a very different concept from a human one. This final phase could last for a while. Betelgeuse could explode tomorrow night, it could explode next year, or it could explode at any time in the next 10,000, 50,000, or even 100,000 years. It is about to explode, in the same way a 90-year-old person is about to die. The end is certain and relatively near, but the exact moment is impossible to predict. There is one final mind-bending twist to this cosmic waiting game. Because Betelgeuse is 642 light-years away, we are seeing it as it was 642 years ago. The light that hits our eyes tonight left the surface of that star around the year 1383, when Richard II was King of England and the world was a very different place. This means that the supernova explosion has in all probability already happened. The star we see in the sky is an illusion, a ghost of light still traveling towards us. The cataclysmic end of Betelgeuse is very likely a historical event, its light and neutrinos already hurtling through the void on their long journey to Earth. If Betelgeuse exploded in the year 1500, we still have over a century to wait. If it exploded in 1850, the show could begin in our grandchildren's lifetime. And if it exploded in 1383, the first neutrinos could be flooding through the Earth right now, and the first light could arrive tonight. We are privileged to be watching a star on its deathbed. It is a cosmic memento mori, a spectacular reminder of the violent and creative cycles of the universe that created the very elements from which we are made. It invites us to look up, to connect with the cosmos, and to appreciate the profound and beautiful violence that seeds the galaxy with new possibilities. Betelgeuse is a promise written in the sky, a spectacle waiting for its curtain call, whenever that may be. All we can do is watch and wait. Look up into the night sky, especially in the cold, clear air of the winter months in the northern hemisphere. There, striding across the cosmos, you will find one of humanity, his oldest and most familiar companions, the constellation of Orion the Hunter. You can trace his famous three-starred belt, his dangling sword, and the 4 bright stars that mark his shoulders and feet. But on his right shoulder, one star stands apart. It doesn't glitter with the crisp white or blue light of its neighbors. Instead, it glows with a distinct deep and fiery orange light, like a baleful cosmic ember. This is Betelgeuse. For as long as humans have looked at the stars, Betelgeuse has captured our imagination. It is one of the brightest and most recognizable stars in our sky, a celestial landmark that has guided travelers and inspired myths for millennia. It is also a colossal, pulsating, and unstable monster. It is a star at the absolute end of its life, a ticking time bomb on a scale that defies human comprehension. And when the internal clock that has been ticking for millions of years finally reaches zero, Betelgeuse will explode. It will detonate in a supernova, a blast of such inconceivable power that it will briefly outshine billions of other stars combined. And when the light from that explosion finally reaches our planet, it will put on the greatest and most dramatic celestial light show in all of recorded human history. It is not a question of if, but when. And astronomers are watching its every move, looking for the signs that the final act is about to begin. To understand the destiny of Betelgeuse, you must first appreciate its sheer mind-bending scale. To call it a star is an understatement. It is a true cosmic leviathan. Our own sun, a star so large that you could fit over 1 million Earths inside it, is a mere pinprick in comparison. Betelgeuse is what astronomers call a red supergiant, a class of star that has reached the final bloated stages of its evolution. If you were to take Betelgeuse and place it in the center of our solar system, its fiery surface would extend past the orbit of Mercury, past Venus, past Earth, and even past Mars. It would swallow the entire asteroid belt. Some estimates suggest it could even engulf the orbit of Jupiter, the largest planet in our solar system. It is a star so vast that its diameter is nearly 1 billion miles across. Its size is matched by its brilliance. Although its surface is technically cooler than our sun's, which is why it glows red instead of yellow-white, its immense surface area means it pumps out energy at a staggering rate. It shines with the light of more than 100,000 suns. If Betelgeuse were as close to us as our nearest stellar neighbor, Proxima Centauri, it would be the third brightest object in our sky, after the sun and the moon, a permanent, searingly bright red lamp hanging in space. This gargantuan star is not a static, stable ball of gas like our sun. It is a dynamic, pulsating, and semi-regular variable star. It is a star that literally breathes. Over a complex cycle of roughly 400 days, its outer layers swell and contract, causing its brightness as seen from Earth to fluctuate noticeably. This instability is a classic symptom of old age in massive stars. It is a sign that the internal forces that have sustained it for millions of years are beginning to lose their equilibrium. This deep, ominous red color and its fluctuating brightness have made Betelgeuse a figure of fascination and foreboding throughout human history. Its name is derived from the Arabic phrase Yad al-Jawza, which means the hand of Orion, or the hand of the central one. In many ancient cultures, from Persia to India to China, its fiery hue associated it with war, fire, death, and great calamities. But there is a fascinating historical clue that suggests its current state is a relatively recent development. In the 2nd century AD, the great Greek astronomer Claudius Ptolemy catalogued the brightest stars, describing Betelgeuse as hypokouros, a term that translates to a pale yellow or tawny orange color, similar to the star Arcturus. Yet today, no one would describe Betelgeuse as anything but a deep, unambiguous red. This discrepancy has led some astronomers to theorize that we have witnessed the star evolve from a yellow supergiant to a red supergiant within just the last 2,000 years, a blink of an eye in cosmic terms. This is a tantalizing piece of evidence that Betelgeuse is evolving at a ferocious pace, hurtling towards its final, inevitable end. The story of every star is a grand battle between two fundamental forces, the relentless inward pull of gravity and the ferocious outward push of nuclear fusion. The life of Betelgeuse is a particularly dramatic chapter in that cosmic war. It was born between 8 and 10 million years ago, a relatively recent event in the 4.6 billion year history of our solar system. It began its life, as all stars do, in a vast, cold cloud of interstellar gas and dust. Gravity pulled this material together into a dense hot knot, and when the core reached a temperature of millions of degrees, the fires of nuclear fusion ignited. But Betelgeuse was not born to be an average star like our Sun. It was born a heavyweight, a colossal blue O-type or B-type star with somewhere between 15 and 20 times the mass of our Sun. And in the world of stars, mass is destiny. The more massive a star is, the more intense the gravitational pressure in its core, and the more furiously it must burn its nuclear fuel to stay alive. While our Sun will leisurely fuse hydrogen into helium for a total of about 10 billion years, Betelgeuse in its youth was a stellar gas guzzler. It blazed with a brilliant blue-white light, burning through its vast reserves of hydrogen in a mere 8 to 10 million years. It lived the life of a cosmic rock star. It was born big, it shone brilliantly, and its destiny was to die young and leave a spectacular corpse. About 1 million years ago, Betelgeuse exhausted the primary fuel source, hydrogen, in its core. This was the beginning of the end. With the hydrogen fusion furnace switched off, the outward pressure that had supported the core for millions of years suddenly vanished. Gravity, the patient victor, began to win. The core, now composed mostly of inert helium ash, started to collapse and heat up under its own immense weight. This collapse raised the core's temperature to over 100 million degrees, a temperature hot enough to ignite the next stage of fusion, the burning of helium into carbon and oxygen. This new, hotter furnace in the core generated a tremendous new wave of outward energy. This energy pushed the star's outer layers, which still contained vast amounts of unburnt hydrogen, far outwards. As these layers expanded, they cooled, and the star's color shifted from a brilliant blue-white to the deep red we see today. Betelgeuse had transformed from a relatively compact main sequence star into the bloated red supergiant that now dominates Orion's shoulder. It had officially entered its old age. But this new stage of life, burning helium, was only a temporary reprieve. Helium is a less efficient fuel than hydrogen, and it was consumed in the star's core in only about 1 million years. When the helium ran out, the cycle repeated. The core, now made of carbon and oxygen, collapsed again, heating up to even more extreme temperatures, hundreds of millions of degrees, until it was hot enough to fuse carbon. This process created a series of heavier elements. When the carbon was gone, the core collapsed again, igniting oxygen, then neon, then magnesium, and finally, silicon. Each of these burning stages lasted for a shorter and shorter period. Hydrogen burning lasted millions of years, helium burning 1 million, carbon burning lasted only a few thousand years, neon burning a few years, oxygen burning a few months, and the final stage, the fusion of silicon into iron, would last for only about a single day. This frantic end-of-life process creates a unique structure within the star, much like a cosmic onion. At the very center is a small, incredibly dense core of the latest fusion product. Surrounding this is a thin shell, where that same element is still fusing. Outside that is a shell of the previous fusion product, and so on, all the way to the star's vast, distended outer envelope of hydrogen. Betelgeuse, right now, is a star with multiple layers of nuclear fire raging within it, a complex and unstable engine that is rapidly approaching its final catastrophic failure. The final moment of a massive star's life is all about one element, iron. Every step of nuclear fusion up to this point, from hydrogen to helium, all the way to silicon, releases energy. It is this released energy that creates the outward pressure that fights against gravity and keeps the star from collapsing. But iron is different. Iron is the ultimate nuclear ash. The laws of physics dictate that fusing iron atoms together does not release energy. It consumes it. So when the silicon burning phase in Betelgeuse's core ends, and it is left with a dense, inert core of pure iron, about the size of the Earth, the star has reached a fatal dead end. The nuclear furnace at the very center of the star, the heart that has beaten for millions of years, simply switches off. In an instant, the outward thermal pressure that supported the crushing weight of the star, its outer layers for its entire life, vanishes completely. Gravity, the patient, ever-present force, wins the war in a final, spectacular and cataclysmic victory. The iron core, with nothing left to support it, collapses in on itself with unimaginable violence. In less than 1 second, a ball of iron the size of our planet is crushed down to a proto-neutron star no larger than a city, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. This spectacular collapse is the trigger for the supernova.